Hello, everybody. Good afternoon. How is the lunch? Good. Hey, my name is Dries Van Laerhoven. I work for ABB. I brought a colleague with me today. His name is Glenn. He will speak the most of the time today, but I'll give a short introduction about what is ABB, how big is ABB, what are we doing, and then Glenn will go in the subject matter of going energy optimization and energy management. That's still correct. So maybe I'll ask you the question, or start with the question first. Who of you knows ABB? 1, 2. And what are we doing? Where do you know ABB from? So mainly electrical equipment. Okay. Anybody else? Yeah? Yeah, all right. So indeed. Sure. Well, a few years ago, we decided that high voltage was not our thing anymore, and we sold our high voltage equipment to Hitachi. They are still residing with us today in our offices in Zaventem, but we are expecting them to move out rather soon. So in the future, now it's already 2 distinct companies, and in the future we will share different locations, or we will have different locations.
It worked just a second ago?
So me and Glenn, we have about $100,000 colleagues working over 100 and more countries. And we have a yearly revenue of almost $30 billion, of which we do most of it in Europe, about a third in Europe, another third in Americas, and another third in Asia and Middle East. And those 100,000 colleagues are working. I'm not sure what I'm doing wrong, Glenn, but it's not working for me. And ABB has a vast history of being first in some things. And first I wanted to play a small video today, but Glenn said that was boring. And since Glenn will be the star of the show today, I decided to play a game with you. I brought a few pages of milestones from ABB. And yeah, let's hear some numbers, and I'll try to say the milestone that was closer to it and what ABB did that year. So is there anybody that wants to start with naming a year? Yeah? 1950. So let me try. So we have 1953 here. In 1953, ABB realized the first data transmission at carrier frequency performed by a BBC. That's our previous name. Over 735 kilovoltage high voltage line to the power station control unit. I have no idea what that means, but maybe Glenn does. So yeah, that's what we did in 1953. If you look at 1901, there ABB builds the first steam turbine in Europe. Anybody else wants to play a number game? Yeah? 1975. Okay, so I have 1978. Is it okay for you? In 1978, ASEA launches one of the first industrial robots. And that brings us to a nice story. So ABB was 2 different companies in the past. We had BBC, or Brown Boveri and Company, and we had ASEA. Somewhere in the 1980s, they decided to merge, And they took the first letters for both our names, and now we are Isaiah Brown Baveri, or ABB for short. So let's move to the next slide. ABB is divided in 4 business areas. We have electrification, without high voltage equipment these days. And far of the most employees work for electrification. So we have 52 colleagues working for electrification. So about half of the company does electrification as a business. What do we have in electrification? Well, we have small switchgear until our medium voltage switchgear. After electrification, we have motion. Motion is our business area that deals with electric motors and drives. So frequency drives, motors from the highest efficiency to very big medium voltage motors. We also do robotics and discrete automation. So we have 21,000 colleagues working with robotics. We have very big robots until cobots. They're doing advanced digital stuff as well. And me and Glenn, we are working for the business area process automation. And process automation, like the name itself says, we do process automation. So our clients, they are big heavy industry. We have a lot of energy producers or water companies in our portfolio. But our colleagues from process industries, they also have pulp and mining, metal as a portfolio. If you look to the structure of ABB, we have the 4 business areas we just saw. And these are subdivided in 20 divisions. So me and Glenn, we work for process automation, energy industries. And our sisters, they work at energy industries. Our sisters work for process industries. And we also have a section for marine and ports and measurement analytics in our business area. Like many companies, ABB is very proud of the values we care. So we have courage, care, curiosity, and collaboration as values. That means we try to steer our teams into that direction, and that makes a priority of our people. So if we see what our priorities are, we have market leadership. We always try to be number 1 or 2 in the markets we are present in. And that brings good opportunities for our people and a drive for continuous innovation. Technology and digital, that's where we are today. In energy industries, we have a division working on digital. Our priority is also people, of course, portfolio management. We try to have as complete portfolio as possible. We strive for sustainability. So sustainability is a goal in our own work, but also in the products we are providing to our customers. And our financial performance, we are still a company, and a company needs to make money for the stakeholders. If we look to what our strategy on digital is, we focus on creating superior customer value. So Glenn will show you a lot of, in the demo, I guess he is prepared. He will show you a lot of applications, and we strive to give the best value to our customers as possible. How we do that? We combine different zones of expertise. We are working with enterprise software. So the software needs to be cyber secure, it needs to be tested well, it needs to be have a long life cycle. You can't just change over your software from year to year. Your customers have invested in it, so they need to be having the value for 10, 15, or even 20 years. And we focus on our deep domain expertise. Like you saw, we have a vast history of domain expertise and being the first in some things. And that's now resulting in very good applications, very good models that we try to create value for our customers. If we look to another priority of ours, that's our people. That's me, Glenn, our other 100,000 colleagues, and hopefully in the future, you. And we strive to have a diverse workforce. We don't want to be, we encourage our employees to think differently, to speak up, and to share their ideas with them, or with us. If you look to what our purpose is making, here I need to step back and rethink a moment. ABB has written a purpose, and that purpose comes together with integrity and transparency. We like to do transparent ways. If you go back in time, ABB has a bad nickname of being the most corrupt company in the world. Yeah, that's maybe not a good sales pitch. I see Glenn laughing. And it's not because we were the worst at what we did. No, it's because when there was something wrong, ABB spoke up. And we said, hey, here it went wrong. We spoke with the agencies and we confessed up. You can't do unintegrity business in ABB, then you're out the door. And you see it in everything we do. We have very strict code of conducts. I think Glenn is becoming a bit sad of all the trainings he has to follow. But yeah, in every business we do, we try to be integer. So integrity is very important for us, and we try to be transparent in the ways we are doing business. My last slide before I give the mic to Glenn is about Formula E. A lot of the things I spoke today are present in Formula E. Our drive for innovation, our drive for new performance, and the need to manage different kind of modules. In Formula E is more like Formula 1, it's more of statistics than driving. And all those statistics come down in modules that handle tires, handle battery, handle charging speeds. So yeah, that was my effort to try to make a bridge to Glenn today.
Thanks, Dries. I'll try again with this. Hopefully it works this time. I think it should now work. Anyway, I'll stay close to the laptop so that I keep in range. Anyway, so given the short time that I had, I still thought it would be interesting to prepare a couple of slides, but just very introductory, a couple of slides, and then I'll quickly try to move on to the demo that we have prepared, so that you can actually see it in real life. Let's say it's still software, so so no physical representation of the solution that I can bring you now today, but yeah, it is what it is. Maybe also a quick introduction of myself. So I have two roles within ABB. I work already there for more than 5 years now within ABB. My main activity is actually R&D. So also on the Optimax platform, as I will be presenting here, which is about 80% of my time, and then 20% of my time I still do technical consultancy, which is basically supporting the business within the projects. Again, as a subject matter expert of this platform. So. Yeah, also, there's still some room at the end to answer some questions that you might have. I was a bit wary of, okay, should I include many equations or not? I decided not to. But you can definitely ask, or I can also send you some nice documentation where you can actually see them in their full glory. Now, again, a very, very high-level first introduction. If you remember anything, Dries also said something about this. So we really want to bring value to our customers, of course, like any company will tell you. But yeah, with this platform specifically, again, Optimax is a software platform. We really want to utilize models, and I'm going to keep calling it models, so we're not calling it digital twins, just models, mathematical models. That we use in many optimization applications. So again, mathematical optimization applications, where we indeed try to reduce costs, for example, try to reduce carbon dioxide emissions, improve productivity, and so forth. So these are really usually very measurable and monetary values that you can bring to a customer. And so these are typically the ballpark figures of what such an optimization application could bring as a real, again, monetary value to those customers. The 100% reduction, that's not for me. That's, I guess, somebody from marketing came up with this. So you definitely will need other things than software to reach net zero, let's say. But yeah, at least you can then optimally control, let's say, that site using that application. Which is then also definitely a big help in reducing the carbon emissions. But again, the 10% cost reduction, that's I would say is more accurate for with and without an optimization application. So moving on. So again, I focused on the technology. So which technology do we use in this in our Optimax platform? Maybe some of you are familiar with this. So model predictive control. So I have two, again, graphical representations of this technology, but it's usually in the name. So you have a model, and I have some more slides on this, which in our case is usually a first principle model, so purely physics based, which is then indeed used in an optimization program. Typically, this is then first linearized, for example, still, or piecewise linearized, to allow for a bit more scalability, which then turns itself into usually a mixed integer linear program. But we have also some applications that remain a quadratic program for you out there. And this is then indeed done iteratively and also with a receding control horizon. So this is a finite horizon optimal control problem, which has its pros and cons. And that's what's also very big pro for this technology is that you can very easily configure the constraints, so the technical limits of the plant of your site, because typically the economic optimum lies indeed somewhere close to those technical limits, as you can also see there on the right. I have three actually, but so two on this slide. Very nice use cases just from literature. You can see there a double inverted pendulum, for example, with obstacle avoidance. So try that doing with normal or classic control theory. I recently had a student actually that tried, but it failed unfortunately. So you use usually a dynamic optimization model to able to compute the control actions, and as you can also see here on the left, the set point also changes midway, and then it also just goes to that trajectory to that position as asked, let's say. On the right is also what you can also see is left is just purely deterministic. But you can also have, of course, a stochastic approach where you account for multiple possible trajectories. What you also can see better there is that you have these predictions that are being made. The optimization problem that then solves the equation. Then you again always take the first equation and then just repeat again. And then you can see that this horizon is receding, so that of course then what's in the past, that's in the past, but then with updated measurements, you then update your forecasts, and then you get an updated control actions. So that's better represented on the right here. Also, maybe what's very speaks to mind is this application. Again, just pure first introduction into the technology, I would say. So this is not from ABB. Probably some of you will know this. Do you know from which company this is? Boston Dynamics, indeed. So this is from Boston Dynamics. So I was actually a bit surprised that they also use model predictive control. They recently showed very interesting work around this, but they also use model predictive control. I thought they maybe used something more data-driven, but I myself as a researcher should indeed know that there are definitely still some hurdles to be took in that space. But yeah, so Boston Dynamics also uses model prefrontal, so that's definitely also speaks to the imagination on what this technology itself can really do. Let's say. So yeah, I briefly already talked about this. Yeah, it's not super, but yeah. So everything starts with your process model, sometimes also called a plant model. Again, we mainly use first principle equations for this. Again, we're also doing a lot of research to make this more data-driven, like, for example, automatic parameter tuning or something. That's, I guess, the first step that we're comfortably willing to take to compare to the full-fledged reinforcement learning approaches that I myself also am doing a lot of research on. But yeah, so this then comes into a dynamic optimization solver, and then typically we stop at calculating, what are then the optimized set points. You typically also have first some disturbance models on the side. I have a slide on this in a couple of slides, so I'll keep it for that. But why, again, typically there is already a control system in place, and a real-time control system. And as you can imagine, there's definitely quickly a scalability problem there, where if you really want to, let's say, overrule or like completely replace the control system, where you really want to have to at real time calculate the manipulated variables instead of the optimized set points. Yeah, again, this quickly becomes very unscalable, and it's very common then to basically have a hierarchical control, let's say, architecture, where you then basically limit yourself to finding the best set points, but then that the set points are still then used in the real-time control systems that basically do an unconstrained error minimization of the measured manipulated variables or process variables that you try to steer towards. So we also use Modelica for this. So I think I have also a slide on this. So this is also a graphical representation. So it's very object-oriented. It's also very user-friendly, I would say. There's also a vast library of specialized equations in the end. But we of course have our own, develop our own models, also using some third-party, common third-party packages. But the point that I mainly want to make here is that, again, in an energy management application, you really have to look at all the energy streams, let's say, in the plant on site, and not only at, let's say, electrical. There are many customers or competitors rather that, for example, are very good in doing electrical energy management. And again, if you didn't notice by now, so what I mean with electrical management is really sending these optimal send points back. So of course everybody knows energy monitoring, but that's just pure visualization. But if you look, let's say, in the market, then everybody has energy management, but in reality, almost nobody has energy management. In the sense that you really send optimal set points back to the underlying control system. So again, energy management is basically energy monitoring plus optimal control, as sometimes also we put it. But again, so coming back to this point, so if you would only look, for example, at electrical, and then if you then look at your natural gas bill or something else, that you maybe fall from your chair. And so by looking at all the energy streams, and then again, I think I have a slide on this. Yeah. This is the only equations that I'll show you, unfortunately. But again, I can share more with you if you want. So this basically boils down to, okay, you will have to use matrices instead of just pure single-line equations. And so that in literature, this is then sometimes called an energy hub or a multi-energy or multi-carrier. There are many names out there, but this basically then allows for an optimization across all those energy carriers, energy streams, and not only, for example, electrical. So this is this is one hint of on how this is then done. But this is definitely not new. This is from 2007 already. So this is definitely already a mature approach in doing this. Then I'll briefly hinted towards this. So again, we use first principle equations. As anybody who works in forecasting or prediction knows that this is maybe not the most accurate approach, and so what you for example also typically do is you also within the model predictive control technology is that you have external states or disturbance predictions, as it's sometimes called, like a very typical example is weather forecasts. Again, we don't have a first principle equation. We don't have first principle equations for weather predictions. Also not for like demand predictions. So these are usually then other disturbance predictions. And so what we now use is something rather simple, but what we recently developed, well, it's also again 2021, so it's already some time ago, is what's also called in literature an automated machine learning approach. It's not only machine learning that we use there, but it was like the first, let's say, space that like automated the entire prediction process, which involves finding features and also selecting which model to use, and then also more importantly tuning the hyperparameters of these models. And so basically what's interesting about such an automated forecasting pipeline, let's say, and again you can read the details in that paper, is that not every system immediately has a very large historical data set. And so what that means is that if you have a green field, and again, so no historical data sets, how are we going to do those data-driven disturbance predictions? So what happens is then, okay, let's say you first have 2 or 3 weeks of data, and then you let your AutoML pipeline run, and then it finds the best possible model and combination of the hyperparameters, which is usually a very simple, like linear regression or an ARIMA model or something like very simple, let's say, and not a full-fledged ensemble with some random forest scene and maybe some neural networks. So you will then do this, let's say, every day, every week, whatever. As more data you get, and so that you also basically are sure that you are always using the best prediction model with the available data set that you have. So this is, again, for these disturbance predictions, like demand forecasting, also price forecasting is typically also done with this, like day ahead or intraday price forecasting. And then I think that are the slides that I have. Yeah. So maybe already some questions before moving to the demo. I hope it was clear. Is everybody familiar with model predictive control or has heard about this? Or yeah, again, so the idea is that, okay, you have so you look again in the future over finite horizon, where you use typically, again, or in the very basic case, first principle equations, in combination with those disturbance predictions that I just showed you, like weather forecasts or demand forecasts. All these predictions together with that dynamic model are then brought into an optimization program, basically, like a mixed integer or a linear program or even quadratic programs, and which is then solved over the entire prediction horizon, but then only the first control action that's closest to the current time step is then kept, and then also actually executed in or sent to the control system, and then we wait, let's say, depending on the application, a couple of seconds, up to, let's say, 5 minutes, 15 minutes for slower processes, and then everything is basically repeated. So that's basically the essence of that technology. But again, yeah. So I showed you some nice applications that, like, for example, even Boston Dynamics has. But yeah, maybe, okay, this is maybe still some vague concepts, and I'm moving on to actual energy management. Um, Typically it starts with such a, again, simple, nice real-time dashboards. Just at this stage, just pure energy monitoring, not actual optimization calculations still involved. And in this use case, I think, we have a CHP. I'm not sure if everybody's familiar with that. We have some solar PV, a battery energy storage system, and then of course the grid connection, which makes sense. And then you can typically also see, okay, what is then demand, and how is this then filled in? So this is just a Sankey diagram, again, real time. What is then, for example, the current energy price? Are there any alarms or warnings in place? Some KPI, and then some other KPIs like how dependable are we on from the grids? How much renewables are we currently using, and so forth. So, yeah, again, maybe anybody who's maybe some familiar with this is this is just Grafana. I'm not sure if you're familiar with that. So where you can indeed make nice dashboards. Again, just pure monitoring of your energy consumption. But then moving on to the actual optimization applications. So again, the same use case here. So we still have a grid, we still have some solar, we have the CHP. What I didn't show there on the overview was we also, of course, have some HVAC. And why HVAC? Because HVAC typically has some sort of flexibility. And yeah, I haven't brought to you this now, but what we mean with flexibility is basically anything or any consumer that we can shift in time. And this can be long or very short, like only, let's say, a couple of minutes or like a couple of hours. Then we have the BESS, the battery energy storage system. Usually there are still some like diesel genset, usually more for backup purposes, but still there are many, let's say, available in the industry. And then we still, of course, have some uncontrollable loads, and then the grid buy and sell prices. So this is called day ahead. And so what you see here, this is the current time step. So indeed 15 past 1. And so this is indeed the future. And so for me, it's always a bit difficult to, it's like, yeah, but this is just like the previous monitoring screen, but what's happening in the background is really a lot. So again, what's happening here in the background is first we have those disturbance predictions over typically 2 to 3 days ahead into the future. Like also solar, for example, is typically also a disturbance model. The load also, it is also just a disturbance model. And then, again, using the dynamic model, the first principle equations of all those assets, like how does it mathematically describes itself, and how does it react to the control actions that we will send to it. And this is then, again, solved over the entire prediction horizon, which you should see here. But then, of course, again, only the current time step is then actually executed. But it's a bit more complex than that. So this day ahead optimization loop, again, maybe saying something else still first. So do you know anything about day ahead energy markets? Ever heard of this? Yeah, okay, perfect. So even though it says in the name that it's day ahead optimization, which is actually multiple days ahead, as I just sent to you, this is indeed confusing also for some of our customers. But it also doesn't imply that you have to partake or participate in the day ahead market. So this also perfectly works if you just have a peak off-peak tariff or something else. But given that this is a demo system and that there are many customers that do have day-ahead contracts, this is what we're showing here. But basically, what you then here try to do is, okay, again, I make these predictions of, for example, solar in feeds, also the prices. When is it most beneficial to, in these cases, charge the BESS, discharge the BESS, to operate the CHP, and then so not only when, but also with how many. And is there still some flexibility, or how can I use the HVAC, for example, as to optimize my objective function? Again, this can be multiple things, as I also briefly hinted towards. Typically, it's usually a multi-objective optimization problem, where we balance out the like pure monetary values with maybe some sustainability goals that the site or the client has. Sometimes we scale it, or just give it fixed weights, and then again it's become a single objective problem again. But yeah, many possible things. We also have grid independencies. Some clients really like that, so there's some usually multiple objectives or combinations of objectives that are possible. But again, so this day ahead optimization. So a lot is happening in the background. The predictions, optimization, a mathematical optimization problem is solved, and then this is the result. But this then typically runs only once a day. Not because necessarily because the energy markets, the day-ahead energy markets only, let's say, closes once a day, but also because we have those intraday loops still in place. And so basically what happens here is it's over a shorter prediction horizon. So you're typically only 1 day ahead, or 1 day and a half ahead, but basically with updated measurements, updated predictions. And if there are commitments being made on the day-ahead market, these are also like used here as constraints, as delivery obligations. Because again, you have to see this as, okay, in the day-ahead loop, you predict and optimize your plant. And this schedule can then also be sent to your energy supplier, basically, that then trades the energy to the actual day-ahead market. And then the energy supplier then basically confirms or sends a schedule back, like, okay, this is what we bought for you, and this is what you then have to follow, at least with the current information that you have. Because, again, predictions are definitely not perfect. So that's why you have those intraday optimization loops, of course. But still, even more importantly, because again, this is just the same thing, but then with updated predictions and measurements, as I said. But what also still happens is, and I don't have really a good maybe interface that shows you this here, but there's also still a real-time optimization loop that's being run in the background at every typically 2 to 5 seconds. And basically that's, again, pure real-time, so no predictions, so pure real-time optimization problem that's being solved. And there it basically looks like, okay, what did we commit, or in the day-ahead markets, were there any opportunities still in the intraday markets? So what do I preferably have to oblige to? Because again, once you buy a certain energy volume, you better consume it, basically, or other way around. You better produce it, otherwise there are some first off losses that you have to take, but sometimes also even penalties that are associated with that. But again, those intraday loops I didn't mention to you. This runs every 5 minutes, so the day hits only once. Let's say a rough ballpark figure of what you want to achieve, but still, let's say with the confidence level enough that you could commit this to, let's say, a day ahead market. But then the intraday loop runs every 5 minutes. But again, in 5 minutes, a lot can happen. So looking at this demo, and what is also very easy to understand, let's say, is that cloud coverage of solar is very important. So if a cloud comes over the building, this has a drastic effect on, of course, how much solar production that there is. And so this cloud can come and can leave within 5 minutes, let's say, or even if you didn't account for the cloud to be there in the first place, and you think you have a lot of sun, you can quickly come into real trouble. And with real trouble, I mean there is, of course, always a grid limit, and so there's only so much you can buy or exchange from the grid. And especially now in the Netherlands, with all the net congestion problems that they currently are facing there, it's really a big problem where you really have to have this real-time optimization loop, because otherwise, if you don't do anything for 5 minutes, then the fuse will definitely blow, let's say. The real electrical engineers here might know that this is maybe not true, because it's not overload protection, a breaker typically, it's short circuit protection. But still, it's not a good idea to exceed the grid limit for any period of time. And so that's why you really have this real-time optimization loop in place. This is an actual quadratic problem, because it basically just looks at, okay, what do I want? What do I measure? And this is just a least square quadratic problem, which then tries to follow what's been calculated in the beginning. But again, if it's not feasible, then you will definitely redistribute the set points accordingly with the last real-time measurements that are available. Another use case is that my battery goes into alarm, or my CHP is down unexpectedly, and then again, if you wait 5 minutes, then again, a lot can happen. So this is not done, of course. This is unsafe. And so you would then more quickly measure and react accordingly within those real-time loops that are still in place. What's also still being done in those real-time loops is if you have any service or like grid service contracts. Here in Belgium, you can have that with Elia, for example. In the upcoming, let's say, also with the DSO now, with Fluvius, let's say, in the near future, you will be able to do this. But there it's like the primary, secondary, and tertiary reserve markets, so like frequency containment reserve, FCR, automated frequency restoration response, and manual frequency restoration response. So maybe if you also heard about those. And then again, so companies can subscribe, let's say, to such a contract with Elia. There's also still a balancing responsible party involved still, but that's maybe a technicality that's maybe not super relevant for now. But there it's pretty interesting, because there it's only about power, because Elia, of course, wants to keep the lights on, wants to stabilize the grid. And so, again, as energy engineers, you know that power and energy is not the same. There is actually a bit of an interesting conflict out there, where I think somebody here, maybe from KU Leuven, is also looking, doing some research on. But anyway, so what you can do here is that, okay, let's say indeed my battery, I have a battery of 1 megawatt power, and let's say 1 megawatt hour or 2 megawatt hours of energy content. But you can say, okay, let's say reserve 200 kilowatts or whatever, 500 kilowatts for Elia, let's say. I also still have some flexible loads. So in the end, you can also, for example, give some priorities on which flexible loads you want to use first. But it basically allows those industrial clients to support the grid when needed, first and foremost, but also to get some extra revenues, basically, because Elia pays big money for this, basically. Especially for frequency containment reserve, I think it's for 1 megawatt. If you have 1 megawatt that you only reserve for them, so then they didn't have to activate this, because you have both a reservation fee that you get and also an activation fee. So 1 megawatt is, I think, 170,000 euros. So 170,000 euros per megawatt per year that you get just having it on standby for Elia. This is then, of course, the frequency containment reserve market. So this is the most, let's say, intense, and also where you have to respond the fastest. But it's, as you can hear, it quickly becomes interesting to also subscribe to those kind of services. Especially having such a advanced, of course, optimization platform in place, where you're then able to indeed respond properly and accordingly. So yeah, that's still being done in those real-time optimization loops. So if such a call comes, then also this amount of power that has been reserved is then also then activated either positively or negatively, because of course you can have over-frequency or under-frequency in the grid. So what I can still show you here also is, these are just some nice screens, or maybe this is already a little bit older, but to speak to the animation, yeah, you can do a lot with again Grafana. Also so we both have a real-time database and also an historian database, so where you basically store the energy-related data where you can then generate reports, analyze, of course, your energy consumption, look at some trends. So how much here there is something missing. Normally there's also some pie charts here, but you get the idea. So like it's nice dashboards and basically reporting, also like generating PDFs and whatnot. Because especially large energy consumers, they also have are obliged to report their, for example, energy consumption and CO2 emissions to the local government typically. And so the industrial reality usually is that they have an Excel sheet somewhere that they frantically update every whatever quarter. And if they have a system like this, then of course they don't have to frantically update this Excel, and then they can just export it from the historian and be done with it. So this also saves a bit time to them. So if you have somebody from sales, he will definitely say, this is also a nice value, so you can save some time with this. But then I will come and I say, I know a real added value are these optimization applications. But again, the industrial reality is that it is also valuable, and you definitely also save some time, of course, with this. I'm not sure what the time, how much time we still have left. 5 to 10. Okay, before the questions, yeah. Or maybe already. Do you have any questions about this specific application before I move on to another one? Yes, maybe here. Yeah. So what do you mean? There are a couple of things. So this is just your estimate. So this is your. Yeah. Huh, that's a good question. That's a good question. I actually don't really have a figure for this. Yeah, I don't have a figure out this other fly. Like you say, I can tell you individually. The predictions. This prediction is typically around this accuracy or what, but I haven't really. I can't give you the figure like this is what we estimated, and then this is what actually been. I don't really have that figure, so unfortunately. So maybe I can maybe check that for you, and then maybe share that around. But I don't actually have the comparison, the real comparison that what you're asking for. I thought you were maybe going to ask like, how do we send those signals? Because that's also, not happens automatically, basically, right? And so there is a lot of engineering still involved in that regard, where you actually have to interface with that underlying control system, and then a lot of industrial communication protocols come into the question, and so. But the actual comparison between the day ahead estimates and then the actual let's say results, I don't have that figure, unfortunately. So good question. Yeah, yeah, yeah.
My first question is about the discrete decisions. I wonder if even the real-time controller can also take discrete actions or just change continuous quantities such as the output power of a generator, provided that the generator is already on, or can also activate a CSB, for instance.
No. It also activates. I'm not sure if it's shown here. Yeah, it's also shown here. So it really also like either activates or deactivates assets if needed. Indeed, and then especially in a CHP, that's interesting because it's not fully controllable between 0 and 1, let's say, or 0 and 100%. So we can typically have like only scale down to, let's say, 50% or even 60% of its power, and then you really have to shut it off completely. And that's where then some binary decision variables come into play to then actually shut off those assets that are not, let's say, fully controllable between 0 and 1. And then it also looks at like, especially in CHPs, and then you have either motors or turbines, depending on the size of the sites. Then you also then look at what are the ramping limits. So you cannot immediately ramp up, let's say, infinitely fast. So then you also look at, okay, what are the ramping limits up and down of those turbines then usually. What also sometimes very common is, or what's also very common is like, okay, if it's activated, then you don't immediately want to deactivate it. And so then you typically have some minimum runtime and minimum uptime, or minimum downtime and minimum uptime constraints that are put in place in order to avoid this. So it can definitely also switch on and off assets, but yeah, with all those considerations that I just gave you. Yeah.
My second question is about the values, provisional values of some quantities at the end of the horizon. For instance, for the battery storage, providing different values changes the forecast about the total amount of energy to be provided or not. So I wonder if you have some particular strategies for handling that.
So what basically happens is, so you have those longer term predictions, and then you indeed get a first battery schedule, let's say. But this battery schedule is indeed then updated every 5 minutes with then the latest predictions and also the measurements from the fields. Yeah, because it has better information, better predictions also usually. So then it basically updates the battery schedule because that's all still in the future, so we are still able to do that. But it also then, of course, considers any commitments, any delivery obligations that maybe already made. Also, again, the grid constraints and whatnot. So it basically does that in the intraday or updates the battery schedule. I don't want to say automatically, but I think you understand what I'm saying by iterating with like over this shorter term horizon. I'm not sure if that answered your questions, like or what you may be referring to is also what's also sometimes being done is like we say, I want to have the state of charge at the end of the prediction horizon to be at a certain value, so that you can also do that. So it's usually not super common because it's basically something that you want to decide upon yourself in the optimization algorithm, let's say, or application. But you can impose these constraints these terminal constraints at the end, where you say, I want it to be at whatever state of charge at the end of the control and prediction horizon. So I'm not sure if that answers your question or.
Partly, it was also specifically about the longest time,
Yeah.
the optimization problem having the longest time horizon.
Yeah.
As you mentioned that it is a receding horizon,
Yeah.
not a fixed horizon.
Yeah.
I wonder if you have some particular strategies to set the value to be reached at the end of this receding horizon.
Well, that was what I was saying. So the no, I think I get your point. Yeah, no, indeed. No, I think I get your point. So again, also in this real-time optimization loop, which also is partly in the intraday loop, but basically what you do is there is a mismatch between your discrete actions typically and the continuous behavior of your underlying system. And so what you do is, it's sometimes called set point tracking, because again, it's only set points that we're still calculating, but it doesn't necessarily translate 100% to then the actual measurement. And so what you do is then what happens is that, okay, you look at, did I reach the set point or not? And if not, you will actually artificially increase the set point near the end of that 5-minute block, so that the volume of the energy that you have, for example, committed on some certain energy markets is actually, yeah, the volume that you actually committed. So I think that's what you're asking, right? Yeah. So it's basically a running sum, let's say, of how much energy you then commit, like either consumed or produced during that discrete block, and in order to account for the difference between your discrete blocks and your continuous behavior of your system. Does that answer? Yeah, there. So it does still, because it really still looks at the current state, but indeed, so the results of the day ahead optimization, they first still go through the intraday and still go first the optimization loop, and also still go through the real-time optimization loop. So there is only always one actual set point that's being sent, of course, to the actual assets, and that is from the real-time loop to the actual assets. But if the actual measurement, let's say, of now is good, and the very near future is also very good, accurately predicted, then there might not be necessarily a correction in the intraday loop and also not in the real-time loop. So then basically the set point from your day ahead loop basically just goes through those intraday updates and also the real-time updates, but doesn't necessarily have to get any corrections with those. But that's of course only just after the day ahead market, let's say, or the day ahead optimization run. Because again, this only runs one time, the day ahead loop. But this is typically around 11 o'clock in the morning. At 1 o'clock, let's say, or a couple of hours beyond this, there are these day-ahead results. They do get heavily, let's say, corrected within this intraday and maybe also the real-time loop that is still being put in place. So it really pushes through, let's say, still those intraday checks and optimization loops and real-time loops before actually going to the assets. Well, very easy. The predictions are not perfect. So solar is very typical, very uncertain. Also, just the demand, prices are not perfectly predicted. Also, just the model mismatch between the dynamic models in your MPC and the actual system dynamics. There is not very big. There is a difference. So there are a lot of uncertainties that arise because of this, which require this shorter term and also this receding horizon to account for this. So yeah, so hopefully that answers your question. But it really depends on the application. But these are some examples based on the demo system here.
Yeah, my question is more about yes.
No.
Sorry. Yeah, my question is more about if you have real-time measurements, you can correct those uncertainties. But during the day ahead, you don't have the real-time measurements. So I mean, no matter how many times you rerun your optimization, it's still the same measurements, or are they also being?
No, so the day ahead is only run once a day.
So it's not an MPC.
So, sorry? Well, is this an MPC? So it's once a day, but then you wait a day and then you do it again. So the day ahead loop has a very long, let's say, control horizon, but it's still receding. Whereas the intraday has a one a day and a half prediction horizon and on a 5-minute control horizon, and then the real-time loop is just real-time without any horizons. So yeah, but so it's still receding, but and the main reason for this is because the market closes. So the market closes at noon, and then you're done. Then you're done. So then you have to do something else. Then it's either on the intraday markets or some imbalance markets or whatever. So the market closes. So that's done. So yes, yeah, maybe yeah. Please do. So you also already consider the same constraints in the day ahead and intraday loops, but still. So it's purely centralized. It's a centralized. It's not a decentralized agent or something. It's purely centralized. So all the data that you need is centralized to this platform. So it's not a decentralized algorithm or something. So it's not like a multi-agent system or anything. No, it's just purely centralized decision application, let's say, or software application. No. So it's decentralized in the sense that at each site you would then have such an application. And then, so we also have and you maybe saw this here already. So we also have a virtual power plant application. But so it basically does very similar things. But yeah, the map is not working now, I see, unfortunately. But basically, that's I think more related to your question. So what you would then have is you would then have at multiple sites, let's say, having such a site energy management application running, and then you can still aggregate the flexibilities that you still have to indeed, again, a centralized decision agent, but then only looking at the flexibilities on a, let's say, much simpler level, whereas then the on-site application really takes care of all the technicalities, all the constraints and whatnot, also this real-time loop and so that I talked about this. But there is a separate, indeed, a virtual power plant application that basically then aggregates and de-aggregates those decisions to those lower acting agent. But so in principle, it's always better to have a centralized with full knowledge, of course, making decisions than not. But yeah, what other market participants are doing, you don't know that. So and indeed, so that might affect prices on the market and whatnot. But that's, yeah, again, the uncertainty that remains in also your disturbance predictions typically. Yeah, of course. Three days. 3 days. No, this is 3 days or 2 days and a half. So this is now. This is you can clearly see this is tomorrow. This is the day after tomorrow. So it's typically like 3 days. It's typically 3 days. The day ahead optimization loop into the future. And so the reason for this is, again, in theory, the further you can look into the future, the better decisions you can take, the more optimal the solution will be. And so physically, the physical representation of this can be if you only look at one day or only have then you don't know, for example, how much sun or what the prices are for the next day. And what you can clearly see here, for example, so we expect a lot of sun 2 days from now. So then it's better to, for example, fully discharge your battery first, so that you can maximize charge, so you can fully charge the battery with that solar infeed that we're expecting. So no, so Yeah. So yeah. Typically, you have a daily pattern indeed, but still, so the only extra benefit that you have is like if you only would look at 1 day ahead, then let's say the state of charge would be whatever, let's say 20% at the end of your prediction horizon, but this might not be optimal for the following day. And so if you look multiple days ahead, then you can also, let's say, fine tune this day ahead, this let's say end of day state of charge of your battery or whatever that you have. But it's definitely true that that the battery is usually like fully charged and discharged in a daily cycle. But so it then really is the end of the day state of charge that you can still fine tune. Because there is, for example, more sun or more, or the prices are better the upcoming day. So there is still some benefit looking further. Let's say mathematically speaking, it's always better. But so let's say physically speaking and looking at this demo, so that's basically the translation of this property, basically, this mathematical property. So this is with the day ahead. So this is with day ahead prices. So. Well, it depends. It looks at everything basically. So it's typically not super easy to really say. Well, you could look at all equations, right? But so. Yes, it looks at the prices, but it also looks at how much solar inventory is there expected. Because again, everything that you produce locally, is typically even much cheaper. But like you probably heard this already in like the media and so as well. It's like sometimes there are even negative prices, and so you want to. That's then of course even better again from a financial standpoint only. But yeah, so it really weighs at all those. Let's say. Also, I didn't talk about this yet, but also the energy efficiency, right? So I don't have this in this demo, but the easiest or the best example of this is like a heat pump, and especially air source heat pumps. So yes, you can have a good price, let's say, or you can predict to have a good price, but if it's then very cold at that point in time, then probably the coefficient of performance of your CHP will be very bad, and it might not be best to fully, let's say, take advantage of that low price. So it really looks at all, let's say, technicalities and in order to reach a decision, let's say. Yeah, indeed. So temperature, yes. Sun, really, it's really local. You really have to imagine how good can you predict the cloud that comes over the building?
So on this 20 seconds, right, you have this beacon in solar, right? But it looks from this that you prefer to sell power to the grid than charge the battery, right? If I read the figure correctly.
So let me take a look at the grid. Yeah, indeed. So you're indeed. So at these points in time, you're indeed supplying indeed to the grid.
That very low there. That's also where you have that a lot of solar.
Yeah, indeed.
And so is there a reason for that, or is it just because the models for the battery make it so that it's more efficient or more cost effective to sell power?
Well, you can also see here that at that time there is also a high price to be expected. So then you indeed typically want to, sell the energy. Curtailment, normally yes and no. Sometimes. So it's not always possible technically to do this, but if it's possible technically, and then you could let's say opt for this. And this is, but it's only like in very extreme cases that you would normally activate the curtailment of PV. Again, the use case that is a very, or where it's then useful is then like if there are negative prices, then of course you want to curtail your solar because otherwise you would have to pay to put electricity on the grid. So then you could opt to curtail your solar PV. Yeah. So it might become more. It might become more. And so again, so technically this is all possible, like on an application level, but this is not always done, and because it's not always needed now, and but yeah. So yes, you could do that. Yeah, you could do that, but you can understand that that's painful, right? And yes. Well, so the value I showed in the extensive summary, so you should, that was the one thing that you should remember. So the value is basically if you would compare this optimal control approach, because again, this is pure optimal control. This is really a mathematical optimization program. If you would compare these to the rule-based control strategies that are usually implemented on, let's say, in the real-time control systems, then you have this 10 to 15%, let's say monetary benefit that you get out of this. So this is purely looking at, okay, optimal control versus simple rule-based real-time. Again, this is usually only real-time. This doesn't look into the future. It doesn't know what will happen the next 5 minutes. And so then you have this, again, very typically this 10 to 15% cost saving that you can achieve. And so for this application, this is just any industrial site, basically any industrial site, because this is let's say abstract enough, and that is usually only like what they call the utilities. And then again, the load predictions are then that's tricky because every company is different, and then you have this that I showed you, this disturbance approach that I showed you in the slides. So it definitely requires that you have these, especially these disturbance models for every site individually. So every site has their own disturbance models that needs to be trained and fitted with their data sets. Also, you need to configure your dynamic models according to their situation. But then, yeah, basically any industrial site. So we have from steel factories till food and beverage. I mean, you name it. Yeah, you're welcome.